I'm about to bring out our next speaker, Jaikumar, who is over at Anyscale. Let's get him to the stage. Hey, there he is. How you doing, Jai?
Doing great, Dimitri. How are you doing?
I'm good, man. I'm excited for your talk. I'm a huge fan of Ray, so goes without saying that I'm looking forward to everything you're about to say. Now, I'm bringing your slides onto the stage, and we've got some multimodal data with Ray.
Awesome. Thanks for the great intro. My name is Jaikumar. I lead engineering at Anyscale. And today I'm going to talk about scaling multimodal data with Ray data. As you all probably know, multimodal data is everywhere. It started with healthcare applications, analyzing X-rays. With sensor data and geospatial data, multimodal data has reached those areas too. Of course, all the industrial automations with IoT and sensors. And these days, with robots and self-driving car, just the amount and quantity of multimodal data has gone into tons of petabytes. And on the market size, it's also growing exponentially. Image from Perplexity, which says that market cap from 1.7 billion to 68 billion in the next 10 years. I actually asked, what do you think about this? And ChatGPT was like sarcastically replied, "Ha! Now I get a chance to fail at just one modality." All right, keeping jokes aside. So the question for us technologists is, what's the best data processing framework and architecture for multimodal data? Let's look at the existing data processing systems. They made some core assumptions around 10 years back that data is mostly structured and tabular. Bottlenecks are CPU and memory. Operators themselves are cheap and lightweight, Java and Scala. On the other hand, AI data processing systems have a different set of core assumptions. Data is now mixed modality, includes tensors. Bottlenecks are not just CPUs and memory, but also GPUs. Operators are heavy and distributed as they need to take care of data across multiple machines. And the AI ecosystem is built in Python. So key is that Ray data is a data processing engine. So let's try to understand why. First, there is tensor data type natively built is based on PyArrow, NumPy, and Pandas. We have readers for images, video, audio, and more. Robust support for accelerators, GPU-based scheduling, support for TPUs. We have optimized GPU in-feed. We can handle CPU-GPU architectures. Because it's built on Ray core, the popular compute framework, the operators are stateful. We can do things like streaming execution to reduce memory pressure. I'll get into it in more detail. And there's ecosystem interoperability. We work with all the major data sources, Hudi, Delta, Iceberg, Parquet, with PyTorch, TensorFlow, and all the LLM serving engines, VLLM for batch inferences. Let's take a quick sneak peek into the APIs. You have the read and write APIs for your standard formats, connections with various data repositories. And then you can do transform operations on them, map batches, etc. And then you have the standard consumption APIs to take the data coming out of the transform. You have the aggregation APIs, group by max, min, standard, etc. All the standard ones. And the biggest delta is you have compute APIs. You can determine number of CPUs, fractional GPUs, how you want to specify the concurrency. This is where the power of Ray actually comes in. So let's take a look at an example computer vision application. Here you're reading images from an S3 bucket. Then you have map batches running across multiple machines for resizing the images. We have two models, a segmentation model and the classification model, each with a different set of GPUs and different set of concurrencies. Then you write images. Ray cluster, this is how it looks like it. The get image is CPU bound. Segmentation model and classification model run on GPUs, and each of them can be independently scaled with just specifying the concurrency. And the write results is CPU bound. The other aspect is that the GPU tasks don't have to sequentially wait till the CPU tasks are finished. So if a chunk of data is ready to be processed on GPUs, it can be streamed to the GPUs, thus increasing throughput and efficiency. All right, let's peel the onions. So let's get into the architecture. Right? So we have got a simple array data API here, read images, you do a map on the transform, you do an inference. So first we define the logical plan and what to do. The read and transform are on the CPUs, the inference is on the GPUs, and the write stages on the CPU. And then the physical plan defines how to do it. It can fuse the read and transform operator, similar because they both run in the CPU, operator that runs on the GPU, and another map operator that writes back the images. One of the key concepts is streaming execution. So basic data processing unit is a data block, array data block. And these operators process data blocks and put it in an output queue. Because it is built on Ray and its object store, access to these data blocks in object store, so that between stages they don't need to be copied. The other aspect is that this map operator, the inference map operator, just like I mentioned before, doesn't have to sequentially wait for all of the load and transform operator to finish. We have also added some enhancements, because on Anyscale we take the Ray Data open source package and we give the infrastructure and the VMs and the machines on it. So you can detect low GPU utilization, you can detect optimized configurations, and make some suggestions around it. The other thing that we noticed was that many times during data processing, you have the fetching part and the data processing part, and these were serialized. We can actually stream the 4.5x reduction in just job startup time. Big aspect in AI system that spot nodes are used and they can get preempted at any point of time. So your system must be handle massive node preemptions. So there's a failure aware scheduler. This is again built in. It provides options, and we have job checkpointing built in so that we are able to efficiently see over here node 2 fails and this job has resumed in node 3. I think that we had was this transition from range-based shuffle to a hash-based shuffle. So in a range-based shuffle, what happens is block to determine approximate range boundaries. Each input data block is split into n partitions. Individual partitions are shuffled, and they're combined with other partitions at the same range. So if there are n is the number of incoming blocks, m is the large target number of resulting partitions, you have an order of n times m. Many times, say, for example, it's 1,000 blocks is n, m is 1,000 partitions, you have 1 million range partitions. And that puts a lot of pressure on the node. Instead, in a hash-based partition method, each arriving block is hash partitioned into key value. The shards are then sent to the corresponding actor. Actors can then combine these shards into new partitions, and then they can also execute join, etc. kind of stuff. So this design allows us to start shuffling part of the operation immediately as the first input block arrives, instead of deferring it until the whole data set is materialized. Check out our Ray Data blog. We actually wrote a detailed blog about this, and we just introduced joins yesterday, which is based on the hash-based shuffle. So to conclude on the architecture advantages, streaming execution, handling back pressure allows us to scale to petabytes of data. Because it's built on Ray core, automatic task retry upon failures. We have a scheduler which handles CPU, GPU heterogeneous architecture. We get high GPU utilization. And the object store that's again built in, zero copy and efficient cross-node data transfer. Let's take an example of a stable diffusion. Right? Here's, as you probably all are familiar with stable diffusion very well. You have to pre-compute image latents and text embeddings for greater than 1 billion samples. This is what it looks like with Ray Data. Again, you'll read the Parquet files. You will do a map on transform images on the CPU. You do map batches. This is the encoder. You can specify the batch size, number of CPUs, the concurrency, and then you write the Parquet back. If someone wants to try this out, this entire example is available on as a template. You just have to you can run it for free, and we were able to show that we are able to reduce the standard cost of stable diffusion by 3.5x using Ray Data. Many companies have used Ray Data. We have Amazon, which was able to see reduce latency, improve cost efficiency. Roblox uses it. Pinterest has seen that they have Ray Data on their GPU-based models. So to conclude, The 2 points I want to make sure um, that people take away from this talk is multimodal data is growing exponentially. Ray data is uniquely positioned to process and scale multimodal data. With that, thank you so much. If you have any questions, feel free to send an email to my email ID. And more details are available on our Ray Docs website. Ray Data has examples, lots of details. And if you want to try out sample code so that you don't have to set up your clusters, just go on to anyscale.com and you'll get all the goodness for free there. Yeah, that's basically what I got. Thank you so much.